Thank you, Karin, for introducing us. I'm with Urs today, and I'm Martin. Welcome all together, and thank you for being with us. In the next 30 minutes, we will show you some important points for a successful system integration of our LGD Compact. We are inspired from our integrators to show you what is important and what is not to do. So here I have our new LGD Compact sensor module. Today we will focus on all system boundaries and show you how easy the integration is when you follow some basic rules. First we look at the sample gas, including flow integration, dust, chemicals and condensation. Then secondly, we consider the ambient influences of temperature and pressure. And at last point, we connect the sensor to a laptop via USB interface and pick out the topic of the battery operation. So first we start with the sample gas and flow integration. Now, Urs, it's your stage.
The LGD Compact is a closed system, and to exchange the gas in the gas cell, you need some gas flow from the point of interest, where is the sample gas, into the cell. So you need just a pump, some tubes and a good filter. That's the minimum. And there are two basic setups. One is with the pump after this gas cell in the gas flow, and the other one is the pump in front of the gas cell. And these have some advantages and some disadvantages. Now first, when you have the pump after the LGD, you can use any pump. But the disadvantage is that the pressure inside the LGD Compact is not well defined, because it will not be exactly at ambient pressure. It will depend a bit on flow, and it will also depend on the filter status. And when you have the pump on the other side of the LGD Compact, then you have no troubles with the pressure because it's always at ambient. But the pump has to be a better pump. You have to take care about absorption and adsorption of the gas in the pump. Otherwise, you will run into problems. Yeah, there is a few interactions in the gas or between the gas and materials of the system we have to care about. And these are chemical or physical processes. One is corrosion, also called rust. And then you lose material because parts of the gas are interacting, for instance, with the walls of the instrument or of any tube. Another one is chemical resistance, and there we talk more about polymers like O-rings. They get brittle or leaky because they absorb parts of the gas and get destroyed after a time. Also, plastic tubes can become leaky after a while when they are not resistant enough. Next item is sorption. Adsorption means molecules are stored at the walls. So for instance, polar molecules like ammonia get stored on the metal surface of the instrument. It's less critical with molecules like methane or, of course, H2 or N2. And it's adsorbed to the wall, and there is also desorption and other conditions where these molecules are released from the walls. This can be triggered by heating or with humidity sometimes. So what's happening in our instrument is that when the gas changes from 0 to a span calibration value, like 100 ppm, the molecules will stick first to the walls, and you will not read the value you're expecting. And then the surface or field, it will not influence anymore what you read. And so the response is kind of delayed to what you expect. And maybe later when you add some humidity to the gas, these molecules are released from the walls and you will get a huge peak. And that's reality. This is not the error of the instrument. So, last item is diffusion and permeation. Give care, some tube materials are kind of partially open to ambient, so you will lose part of your gas by diffusion or permeation. So for instance, methane can go through the walls of a silicon tube. Don't use silicon tubes for methane. Now, the most important thing about all this, note very well, it's not just about the reliability of the system or destruction of some parts. When there is interaction between the gas and the system, you will losing some of the molecules, so you will not measure the real sample gas you're interested in. At least it will be delayed, but maybe you will read a smaller value than expected. And that's important over all the gas flow from the sample point into the gas cell. What's afterwards, we don't care. Okay, next item is condensation. Condensation is something everybody knows from daily life, especially guys who wear glasses like myself. When you walk indoor from outside in winter, or you know it from your car, and so on and so on. This always occurs when water vapor touches colder surfaces. It cools down and it makes little liquid drops. And the consequence is that this makes you kind of blind. You cannot see anymore what you like to. We have two windows on our gas cell, and if they have condensated water drops on it, our sensor gets blind as well. One example from applications. Some people want to measure the ammonia in a pig stable. And typically inside the pig stable, the air is warm and very humid, and there is some ammonia. And also typically all the control system and the measuring instruments are mounted outside the stable, where at least in wintertime it's pretty cold. So when you suck the air from this hot, wet area into the sensor, you will have condensation and it will not work properly.
Hey Urs, this was a spoiler. The ammonia sensor will only be launched in a few months. But never mind. How to avoid this condensation inside the LGD Compact?
That's not so complicated as it sounds first. The most simple system is just the LGD Compact plus a filter and a pump, and you take care these parts are warmer than the dew point of your sample gas. And we would recommend to keep the sensor in the area, in this case, where you measure, and to put it in a warm corner, or to mount it inside a housing, and the energetic losses of the compact will heat up a bit this compartment. That's enough. That might be okay.
And what would you recommend in a more challenging application where the sample gas is really high humidity and the sensor is mounted outside?
Then it gets a bit more complicated, but there are some simple rules of design you can follow also. Yeah, this solution, still pretty simple, is to add a water trap, also called condensation pot, near to the end of the gas tube line, below the area where the LGD Compact and the whole system is mounted. And in there, all humidity is condensing, so it will not go into the compact. You put the water trap down on the wall about 1 meter or more below the LGD Compact, and then it's impossible for the pump to suck in water. That's an old trick from the greenhouse gardening business, where you measure a lot of CO2 and it's very warm, very wet inside, and the instrument is always outside the greenhouse. Also recommended for this setup is to add a hydrophobic filter, like Gore-Tex or similar, at the input of the LGD Compact. Just in case of something is going wrong, it will block water drops. Also, keep attention to lay out the tube from the sample point to the water trap with continuous slope. If you have any siphon-like curvature, you would collect water there, and it might stop the gas flow. Anyway, when it stops the gas flow, the unit will not work correctly anymore, so it's a very good idea to add a simple flow gas detector to the system. And if the system is clogged somewhere or the pump is not working correctly anymore, you will realize that you do not measure anymore the sample gas you're interested in it, but you would just measure the always same gas which stays accidentally inside the gas cell. And that's not what you like to do. Next item is we talk about dust, and in contrary to condensation, dust would reduce the performance only a little if you have a little bit of dust, but also it can sum up over a long time, and after this long time you will have a lot of dust on the mirrors and on the windows, and you will lose a lot of signal. You get first a noisy signal, and after a while it will not work properly anymore. So, what's to do? Use always a filter or a filter system with several filters to reduce the dust load to a practicable minimum, so the gas entering the gas cell has no dust inside. So typically you do several filters, one after the other. First one with big pore size and a huge surface, or a 3D filter, and then you do a smaller one, and maybe the last one is a 10 micron. And it's also recommended to use, at least for the last one, a hydrophobic filter which will block humidity. What you have to take care about also is if you have chemically active gases in the sample gas, take care about the chemical resistance of the materials of the filter housing and the filter membrane itself. Anyway, the suppliers of such filters and filter systems, they will know exactly what's important about the choice of your filter for your application. Now I'll show you an example what you should not do. One of our customers had a clogged filter, and he realized there is no gas flow anymore, so he just removed the filter and put the gas tube directly to the sensor. And then the sensor was the filter, and look what happened. It was filled with fluid and dirt, and after a while it did not work at all anymore. Needless to say, in such cases, this is not replaced for free and a warranty.
Okay, I think we got this. Before we start with the second topic, we will show you a simple construction of the first shown system design. I will now connect these components in the first step. So the filter is connected to the pump, and the pump outlet is easily connected to the inlet of the LGD Compact. and I connect a further tube to the outlet of the LGD Compact. As you can see, this is more or less plug and play and not very complex. After the third topic later on, we will connect also the electrical part. So please Urs, continue with the second part, the ambient influences.
Okay. Many customers are asking about the temperature influence on our sensor. It's an easy question and difficult to answer. I'll show you a temperature influence measurement of a LGD Compact, one to measure methane in this case, and you'll see there is some fast noise on the signal we measured and some bumps. So you can improve this a bit by adding some averaging, and then you get a much smoother curve. And what you see now is, first, there is no slope. There is no slope of the signal with the temperature. And this is because we measure the temperature and we compensate for any temperature influences. So there will be no slope over a wide range of temperature. But what remains are these little waves you see. And these artifacts can be misunderstood as absorption lines. But in reality, they are fake.
And can you explain where these artifacts come from?
Ooh, now we have to go into real science. Getting complicated. Look at the system here, drawn in black. There is a single mode laser emitting one specific wavelength, in the near infrared in our case. This beam goes through the gas cell and is measured by the photodetector. Now, if for instance there is some reflection on the two windows of the gas cell, another second optical pass is possible, shown in red. And this pass goes from the second windows back to the first and back again. And then at the end, near the photodetector, you have two waves, and one is delayed to the other one, and they mix together. So these standing optical waves, they can add or delete. The maximum can be reached when you are in phase, and the minimum when you're completely out of phase. And what is important is that the wavelength is only 1650 nanometers in the case of a methane instrument. That's 1.6 of a thousandth of a millimeter. That's very small. So the real challenge is that the distance between these two windows, which defines the delay, depends a lot on ambient temperature, because the material holding the two windows will contract when you cool it down, or vice versa. And when it changes only 1,000th of a millimeter, you can walk through full wavelengths. Now, when you're measuring a gas spectra like we do, you will get some extra fringes or artifacts, and you might misunderstand them as absorption lines, but it's just fake. And in this figure here, you can see a measurement of the absorption versus the wavelength. And first, without any reflections, you get this curve shown here in black with one peak of absorption at the right end of the curve. But then when you add some reflection to it, then you will get these waves shown in red here. And in this specific case here, it would add to the signal, and you would think you have a much higher concentration of gas than you really have. But depending on distances, temperature, and so on, this could also go in the other direction. And both facts are not so great. Okay, to test such effects, a temperature ramp is a good idea, because when you change the temperature slowly, the delay of these reflected waves is increased, and so the interference with the main wave leads to a wave pattern, and you can see this in the output signal of the instrument. So this is now a measurement with a LGD. There's a temperature ramp over 5 hours, going from 5 to 55 degrees Celsius. And this green line is the concentration measured. And you see there is some little noise on it. And in this case, it's a very nice sinus-style wave visible. That's what we were talking about before. Now, it's not that much, this deviation, but what are the solutions to make it small? Solution one is make the amplitude of this wave as small as possible. And most important thing is try to have no reflections by design. And this we try to make a job as good as possible to realize that. And then on the other hand, take care, no condensation on the windows, no dirt in the cell, because this would increase the reflections. But then there is a completely different idea, and that's the solution number two. You stabilize the temperature of the cell, so you're freezing these waves, or étalons as they are called. And then the modulation you get by the real ambient temperature gets very small. And I will show later on how you can realize this easily. But now, let's show what happens. First, we look at an instrument which is at a very, very stable temperature with variations below 0.1 degrees C. And then you see that there is a little fast noise on the unit's output. And this means the sensor's accuracy is limited by noise. You can improve the accuracy by adding some averaging, 10 or 30 seconds or whatever is okay with your application. And you see that the curve getting thinner you get there. When the temperature is not so stable, it's more complicated. And we have done an experiment in the lab to show the influence of this temperature instability. We have used a simple on-off control to stabilize the temperature of a housing around the LGD. And depending on the hysteresis of this controller, you get a temperature modulation of 0.5 C, 1 C, or 2 C, kind of wave style, and you can easily see what happens to the sensor's output, what concentration is measured. When you are at 0.5 C, the fast noise you always have is still dominant. But when you go to 2 degrees C modulation of the ambient temperature around the unit, this modulation caused by the temperature varied étalon is much bigger than the noise. So the sensor performance is limited by the stability of the temperature and not by the averaging time. It doesn't help to average more when you have this effect. So best is to average a bit and to stabilize temperature if needed.
And also, how can you stabilize temperature in a simple way?
I have a simple recipe here. Take one LGD Compact, a pump, a flow meter, and mount everything together in one closed housing. Now you add at least one temperature sensor, a fan and a heater, and a simple temperature control. Maybe you isolate a bit this housing, and then you control the temperature you measure inside the box and try to make it as stable as possible. Depending on the conditions around this system, you have to add ambient air with the fan from outside to cool down inside this box, or maybe the fan is only needed to circulate the heat inside the housing. All this is not real rocket science, but it has to be carefully adapted to the conditions of your application.
Okay, thank you. That seems not so critical for me. So some customers, they ask furthermore for pressure influence. Do you have some details here?
Yeah, of course we have information about pressure influence. There is two physical effects causing pressure influence. One is the increasing density of the gas. There is more molecules per cubic meter, and this increases with pressure. And the other effect is that with increasing pressure, the absorption peak gets broader and the height of the peak gets smaller. These two effects have opposite signs, and so the influence is acceptably low because they cancel out one another. Let's talk now about the cause of different pressures. Yeah, the local pressure depends on the altitude above sea level, and you lose about 12 millibars of the pressure per 100 meters of altitude change. And our sensor will react with a change of minus 0.4 ppm only when you measure at 100 ppm of methane, for instance. And this influence can be reduced to 0 when you recalibrate on stage where you use the unit. And the second influencing the pressure is the weather. The weather changes maybe 1 or 2 millibars per day. It can vary, worst case, plus minus 15 millibars over the year. And this would give an output change at 100 ppm of methane again of 0.5 ppm.
And is there the same influence for every gas sensor unit?
Yeah, that's pure physics, so it's the same for every unit. And even if you think it's too much influence, you could add a pressure sensor and compensate this influence. Okay, please note, very important, that there is no pressure influence on the 0 level. The 0 is very, very stable.
Okay, thank you for explaining about the backgrounds of the ambient influences. Let's switch now to the third topic, the power supply and the data communication.
Okay, what is a minimal system you could design to measure gas? This would be one LGD Compact. What do you need else? That's a small computer for data storage or for communication, something like a Raspberry, or it could be a cell phone. It has a serial interface at 3.3 volt levels, like our mainboard has. Then you would need a battery to supply the LGD Compact and also this little computer. And you would need a small pump, which is not shown on this picture. And all this will work at voltages of 3.7 to 5 volts DC. And this can be done with a power supply from the mains, or you use a battery for the mobile system. But then you have to think about what's important features of this battery. What are the requirements for the battery operation? We know that the ambient temperature outside can be -10 to 60 C. And the voltage supply needed for our interface board can be 3.7 to 5 volt DC. Below it does not work correctly. Above 5 volt it gets too hot and will not work correctly after a while. And then you have to think about the power consumption. That might be 1 watt for our unit and something for the little computer and something for the pump. And maybe you want to work for 10 hours work shift, so you have a full battery, and when you go home in the evening, it's empty, you reload it during the night. This would define your capacity. Now you look at lithium-ion batteries. Nominal voltage is 3.7 volts. That's perfect, isn't it? But it's not as easy as it looks first, because when you look at the voltage you get from such a lithium-ion battery, this voltage will depend on the discharge level you have and also a lot on ambient temperature. So at 25 degrees C, you will only have 80% of this capacity, and at freezing point 0 degrees C, you will only have 40% of this capacity. So you either have to take a huge pack, or you can not work all day with this package. Another solution I would mention is take 2 batteries in series, resulting in 7.4 volt, and reduce this voltage with a DC-DC converter to, let's say, 4 volts. This is also very stable, but that adds a little bit of cost to this solution. With nickel metal hydride batteries, it's about the same, but the challenge is a bit bigger even, because the capacity is more depending on the discharge capacity left and also more on the temperature. So this is possible. It was done already by some customers, but you have to do this carefully, as always.
So thank you, Urs. Now I think we have enough information to complete our system with the electronic part to a working system. So first of all, I connect the electronic box to the LGD Compact. After this, I have to connect our combined cable on one side to the electro box, and there's already one power supply connected. The other end is the cable with the USB plug, and this is inserted into a separate laptop. Now we can show you first steps with our Axetris software Urs, can you please open it?
Yes, you can download our interface from our internet site. This I've done, of course, before, because that takes some time, and I will start now this interface. When you have opened the interface, you can choose the COM port. You have connected your LGD to the PC. Or you can use the search function. It will try to find any connected LGD. If there are several, you can choose the correct one. And then, when it's connected, you will see the measurement results. If there is more than one gases, then you can switch on the second one by clicking on this one. And you can remove it again with clicking again on it. And below the measurement results, you will see some status informations. They are empty now because everything is perfect.
Thank you, Urs. Very good demonstration.
You're welcome.
If you are interested in more detailed instructions, please find our operating and integration instructions on our website. Our engineers spend a lot of effort in this document to give an answer to nearly every question.
Now we are at the end of this session. I would like to summarize a bit. Proper integration is key for successful use of the LGD Compact. And the proper solution of integration depends on your application, which you know much better than we do. So you have to design the overall system. Our job is to make the best sensor and to support you a bit to integrate it. And don't be afraid. All our customers have found a great way to integrate.
So thank you for listening, and feel free to ask any question in the upcoming question and answer session. Of course, we are also available at the coffee table later on after the next study case. Thank you.